right, students, welcome to the next part of this video for 3.4. And what we'll be doing is continuing in our discussion over velocity acceleration, how this relates to calculus. So just a couple of key statements here. When the velocity is positive, that just means the object's traveling in a positive direction. And you can be north, south, east, west. A lot of times we just define which way is going to be positive and negative. So you might think of north on that. And then the next thing is if the velocity is negative, then we're going in the negative direction, which may be down south. Okay, and then acceleration works like this. If acceleration is positive, just means the object is speeding up. Okay, when you press your accelerator in your car, that causes the car's engine to rev up, and therefore your speed revs up. Okay, and when acceleration is negative, then you're slowing down. That would be like if you hit your brakes. Okay, so the position function, let's just look at this example. Let's say that this is a position function represented by this cubic function, and this gives the position in miles of a freight train where east is positive and t is measured in hours. So we're going to answer a couple of questions about this. This says, first of all, determine the direction the train is traveling when s of t equals 0. So the first thing we got to do is figure out when this happens. So take your function f for s of t and set that equal to 0, and then we need to solve that equation. This could be solved by factoring. It looks like you can take a t out of that. So you would have t times t to the second minus 8 is equal to 0. Okay, so you would find different places then where this position is 0. And that could be thought of just at the beginning of your journey or whatever, or back home maybe. Okay, so we just set each of these equal to 0. So we have t equals 0, and we have t squared minus 8 equals 0. You can add 8 to both sides, then do the square root of both sides. And of course the negative answer for time won't make any sense. I just want to show you that technically that's what you do when you do a square root of both sides. Okay, so now I'm just going to get a decimal on this, so I'm just going to go square root of 8, maybe round off to like 2 decimals. Okay, so what happens then is s of t is equal to 0 at t equals 0 seconds, and t is approximately, let's say, 2.83 seconds, like that. Okay, so that takes care of that. First of all, now it says determine the direction of the train, the direction the train is traveling at this point in time. Okay, so the second main thing we're going to do is we need to do the velocity. If we want to figure out the direction, then we need to figure out if the velocity is positive or negative. Okay, so how do you find the velocity? Well, the velocity is the first derivative, which would be 3t to the second. Okay, so let me write that down. V of t would just be the first derivative. So that looks like that is going to be 3t to the second minus 8. Okay, and then what would happen here is we're not going to worry about time equals 0. We're going to worry about some positive time on that. So we're going to go ahead and do v of 2.83. So we do 3 times, and plug in that time. So I'm going to do 3 times 2.83 to the second minus 8. And then just work that on a calculator and see if we get a positive or negative answer then. Okay? So it looks positive, so let's find out. All right? So I'm going to go ahead and just go 3 times 2.83 to the second power, and then minus 8, okay? And that looks like that's positive, okay? So the velocity at this point in time is about 16, and let's see, this is miles per hour, okay? So since it's positive, therefore, we would say that we're going to the east on this problem, because that's what the problem is saying, basically, is east is the positive direction. So that's the conclusion. That's how we would figure that out then. Okay? All right? So I'm looking at a positive time, because time equals 0 would just be at the very beginning. Okay, so that's what I'm doing. So the next part of this problem, we're determining the direction the train is traveling when the acceleration is 0. Okay, so first of all, what you got to do on this, again, is we have s of t was given as t to the third minus 8t. So v of t would be the first derivative. And we already did that, so that would end up being, on this, that first derivative would be 3t to the second minus 8. The acceleration is the second derivative. It's the rate of change of velocity, so that's s double prime of t. So that would just be 6t. Okay, so we got our acceleration. Now what this says is determine the direction the train is moving when this happens. So we got to figure out when the acceleration is equal to 0. Well, the acceleration is 6t, so we just want to set that equal to 0. And then we can solve that equation then. Of course, if you solve that equation, you would end up getting t is equal to 0. So that's when that happens, is the acceleration is 0 at the beginning of the journey. Okay? Well, and we didn't do that on this first problem, but what we could do now is that is the only place where that happens, is at when time is equal to 0. So we just want to plug that in to the velocity function, see. Okay, so the velocity, we're going to do v of 0, plugging in here, that would be 3 times 0 to the second minus 8. That's equal to negative 8, and it actually would be miles per second squared. Okay, so what that would mean then is we're going the opposite of east. That means that we're going west, because that's in the negative direction. Okay, and they are defining west as negative and east as positive in this problem. So that means we would be going west at that point in time. All right. Okay, so we got that. And the next thing we're going to do is determine the time intervals when the train is slowing down or speeding up. And that is talking about acceleration. So basically, we're going to be slowing down when what happens? What happens to the acceleration when you're slowing down? It's less than 0. It's negative, right? Okay. What happens to the train when you're speeding up? So if you're speeding up, what's happening to the acceleration? Okay, acceleration's positive. Okay, all right. So what we would do on this then, okay, so the acceleration is 6t. Okay, so we're going to solve a couple of inequalities. Slowing down is going to be when the acceleration is less than 0. Well, that would be when the time is less than 0, so we can't have that. So we would just kind of have to conclude that we're never slowing down, okay, because time can't be less than 0. Okay, now speeding up, we're going to do the acceleration, which is 6t greater than 0. So we just divide by 6. We get t greater than 0. So that's going to be when we're speeding up. And we're doing a time interval on this. So if you look at the direction, whenever the acceleration is positive, we're speeding up. Okay. So what we would say on this is we would just say speeding up. As far as an interval, we would say on the interval 0 to infinity. Okay, like that. All right. So it's just whenever time is greater than 0. Okay, I'm going to close off this problem by doing a graph. So I'm going to pull up my calculator, and it's good to graph these things to kind of get a sense of what's going on here. So I'm going to go ahead and put in the position function and just show you a couple of things on here. So let's see, I'm going to go x to the third and then minus 8x, so that's our position function. And let's see, for a window time, I'm going to go ahead and use a negative number because I want to kind of interpret what's going on in this problem. Let's just do a standard window, zoom 6 to start with. So that's a cubic function now. Okay. So if you kind of look at what we found here, is we were determining the direction the train is traveling when s of t is equal to 0. So s of t was equal to 0 at 0, and I think we also found 2.83. So notice if I trace at 2.83, that was about the square root of 2, then you can tell, okay, that's where that displacement's 0 because it has a y value of 0. So that kind of verifies that and everything. Then we determine the direction when the acceleration is 0 on this. Now, one thing that's happening on the velocity on this, and I'm going to move this over just kind of the side here. Let me move my graph over here to the side so I can write over it and kind of talk about what's going on here. So this is s of t. That's your position function like that. Now the velocity, and we're only going to worry about positive time here. The velocity is negative here. So what you'd have is kind of negative velocities there. Then the velocity would be 0. Then you would start having positive velocities, because remember, the derivative is a slope of a tangent line. So basically from 0 seconds to that minimum right there, you've got a negative velocity. So that means that you're going in the negative direction. And then what you're going to do here is from this point, from that point on, then you have a positive velocity like that. Okay, now let's graph the velocity. So I'm going to take this off. The velocity function was the first derivative of this, so that was t to the third minus 8, or t to the second minus 8. So I'm going to put in 3x to the second minus 8, and just graph in the same window. So this is a graph of the velocity function. And what I want you to notice on this then is this pretty well is going to match up with what we found here. We have a negative velocity from here to here. All right, and that's what's happening there. The velocity is negative here, and that's because it has negative values. Okay, remember in this case, the slope of the tangent line is the velocity. We expect the slope of the tangent line to be negative from 0 to whatever that point is. Okay, so from here to that point, we have negative values on the velocity. And then from this point on, we had positive velocities. So notice on the graph of the velocity function, we're above the x-axis. So velocity is positive at that point. And then here, we are below the x-axis. So we're going to have the velocity be a negative. Okay, so that's how that goes. Now, acceleration is the rate of change of velocity. So think about this. If you were doing the acceleration would be the slope of the tangent line on this. So notice the slope of the tangent line here would always be positive. That's what we found. When time's greater than 0, we're always speeding up. So basically what's happening is acceleration's positive. The other way you can look at this is, let's just graph that function. So the acceleration was 6t. So if I graph 6x in a standard window, this is the graph of the acceleration function. And then this basically looks like this. So notice that the acceleration is positive here. So this is a of t is positive. It's above the x-axis whenever t is greater than 0. So those graphs really verify everything. You want to try to get in your mind the position function. Just think of it this way. The velocity is negative from here to here, that point to that point, because you have a negative sloping tangent line. The velocity is positive from here to infinity because you have a positive sloping tangent line. If you graph the velocity function, that should match up with what this is saying. You have a negative tangent line here, therefore the graph of your velocity is below the x-axis. You have a positive velocity from here to infinity, so from there to infinity, the velocity's y values are positive, so it's above the x-axis. And then the acceleration is the derivative, the rate of change of velocity. So notice the slope of the tangent line would be positive from time equals 0 to infinity. And that's what we found out. So this really verifies everything that we saw in this problem. And really what's happening on this is we found that when the velocity at 0 seconds, we're going in the negative direction, so we found that. So everything is verified there, okay? All right, so you got to think about that a little bit, and this next example is going to help you think through that a little more, okay? So these are just graphs now, so we're going to answer some questions about this. And we're also going to graph the velocity. Okay, so basically the velocity is positive. You can kind of think of this when the slope of the tangent line is positive, okay? So this would be a position function right here. That's a position function. So the slope of the tangent line would be positive from 0 to 10, okay? So we're just going to kind of write this as intervals like this. Now, at 0, okay, that slope is positive right there. So we are... the velocity is positive right there. So bracket the 0 and include that, and the same thing at the 10 at that point in time. Now that's kind of a sharp point where the velocity is going to change abruptly. So when we get to 10, we have a sharp point, so we're not really differentiable there. So I'm going to put a parenthesis there then. So the velocity is positive there because you have a positive sloping tangent line, okay? Where's another place where you have a positive sloping tangent line? Right here, from 40 to, I guess that would be about maybe 55. So we'll say the same thing on this. Okay, so the other place is going to be at 40. Again, you have a sharp point, so you're not differentiable there. So we say that, okay. Then when we get to the 50, okay, at that point in time, you do have a positive sloping tangent line, so you have a positive slope there. So that's at 55 like that. You don't have to really worry too much about the parentheses and brackets at this stage, so it goes like that. Okay, when is the velocity negative? The velocity is negative whenever the slope of the tangent line is negative. Okay, remember, this is a position function right here that you're given. So right now you have a negative sloping tangent line. So from 15 to 40, it looks like the velocity is going to be negative. Okay, that just means you're changing direction. When is the velocity 0? That would be when the slope of the tangent line is 0. Okay, so that would be when you have a horizontal line, so that looks like between 10 and 15 seconds, that's when the velocity is 0. Okay, and I'm not going to really include any of those endpoints on that when you do that. You don't have to include the 0 either. That's when the velocity abruptly changes. Okay, so if we were to go through and graph the velocity, then it would go like this. This is kind of what I want you to look at. So from 0 to 10 seconds, let's see what that slope is. The slope is the rise over the run, and I can't tell on here what those numbers are. I'm assuming this is 10, 20, 30 is what I'm assuming that's going to be. Let me just write this like this. Okay, so 10, 20, 30, 40, like that. Okay, so it looks like the rise from here to here, the rise is 30. And it looks like the run is over 10. So it looks like that is going to be a velocity of 3 units. And I think this is meters per second, if you look at the graph. Okay, so if you were graphing this then, if this is 10, then what we would say here is the velocity would have a value of 3. So it would just be straight over. And I'm going to use bubbles kind of like this then. Let me zoom on this just a little bit. So that would go like that. So that would be the velocity there. Okay, that's about 3. All right. Then we want to go from 10 to 15. So from 10 to 15, the slope is 0. Okay, the slope of the tangent line 0 there. So from 10 to 15, we'll just, put a vertical line on the x-axis. So that's kind of going from 3 to a slope of 0. Then from, it looks like 15 to 40, okay, let's figure out the slope there. Okay, so let's do the rise. Now this is just 10, 20, 30, 40, 50. So it's down 50. And then the distance between 40 and 15 is 25, right? So if you have 15 plus 25, you get 40. Okay, so that means that slope is -2. So what you would have here is all the way from, and I think I didn't quite graph that right. I think I did something wrong there. Having a little trouble seeing. Okay, so the slope was 3 from 0 to 10. So that thing should have went all the way over like that. The slope was 0 from 10 to 15. So that should go like that. Now the slope is -2 from here until you get to the point where the tangent line slope changes again. Okay, so that's how that goes then. All right, so you have a slope of 3, a slope of 0, a slope of -2, and then from here on out, we have a positive slope again. So from 40 to 55, the slope is going to be up 10, or no, up, this is 10, 20, it's over 20, up 20, and over 10, 15. So that would be about 1.5. Okay, so what we would do here then is just go up 1.5 all the way to the end like that. Okay, so that's how I interpret everything based on that graph. All right, so think about that a little bit. Okay, so I'm going to pause this just for a second. All right, so that'll take care of that. I made a mistake here, though. I was just looking over that and making sure everything's right, and I caught this. That's about 1.3. Okay, so that's what that is. 20 over 15 is 1 1/3. Okay, so I'll take care of that. You want to know how to look at a graph of a position and estimate the graph of the velocity. Okay, I'm going to go to the next page and we'll work a little bit with this example and just another graph. This is a graph of the position function s of t. Looks like we're in meters here, and it looks like we're in seconds here. So we're going to name intervals on this. When is the velocity positive? Okay, so again, it's when the slope of the tangent line is greater than 0. The velocity is positive when the slope of the tangent line on a position is positive. So when does that happen? You have positive sloping tangent lines. Right there, that's positive, positive. When you get there, the tangent line, the slope of the tangent line right there becomes 0. So what will happen is from here to here, you've got a positive velocity. So it looks like on this, we'll go from 0 to 15. Like that's 15 seconds. Just use an open interval on that. Okay. And then when is the velocity negative? Okay, well the velocity is negative when the slope of the tangent line is negative, when that's less than 0. So that would happen if you look here, so you have a negative sloping tangent line from here until you get there roughly. So what's going to happen is from here to here, when it starts leveling off, now it's kind of hard to tell when that levels off. I'm just going to assume that you still have a negative sloping tangent line until you get right here. Okay, so it looks like on that, that's going to be from 15 seconds until you get to, let's say that's 25, let's just say 27, let's just say 27. Okay, just approximating on that. That looks like that's when the velocity is negative. Okay, when is the velocity 0? Okay, the velocity is 0 when the slope of the tangent line is equal to 0. So that looks like that occurs from 27 seconds to to 30 seconds. Okay, so what you want to look at is positive velocity here, because you have a positive sloping tangent line. Okay, the velocity is also 0 at time equals 15 seconds. So that's one other place where the slope of the tangent line is 0. Okay, all right. Kind of hard to tell here. It might also be, it's probably the slope of the tangent line at 0 is also 0. Okay, so we could also say at t equals 0. Okay, so that would give that then, and then you would have a negative velocity in there, and then you have a 0 velocity when you get there. So 0 velocity there, 0 velocity there. Okay? Okay, so that's it. That's how you do that. Now what we're going to do is sketch a graph of the velocity function below, and we're just going to try to estimate this the best we can. And I'm going to draw over this thing when I do this then, okay? All right, so the idea is from 0 to 15, we have a positive velocity. And that means that from here to here, if we graph the velocity will be, the values will be above the x-axis, okay? So remember, we're trying to estimate a graph of the velocity, okay? Then what will happen from here to here, now you're getting into negative sloping tangent lines. So from here to here, the velocity is going to be below the x-axis. Okay, and then the other thing you would have is right in here, okay, the velocity would be 0, so you would just have a horizontal line there. And what happens on this is, so you just think of what's going to happen here. You're going to start, the other thing is where do we have 0 velocity? So it looks like the velocity is 0 at 0 seconds, 15 seconds, and I'm estimating at 27 seconds. So a good way to start this graph is like this. Okay, if you have 0 velocity, that means the graph of the velocity function will be on the x-axis at those points right there. So that's where you have a velocity like that's 0. So what's happening here is the velocity gets bigger for a while. Okay, you have positive velocity, so your velocity function is going to kind of be going up like this. When you get to this point, it's still positive, but it's decreasing. The slope of the tangent line starts to decrease towards 0. So that would kind of do something sort of like that. All right, so that would be kind of what the graph of the velocity looks like in that region there. Now you're going to have negative velocities, and what's going to happen here, so all of this region here, you're going to be below the x-axis, and then when you get somewhere in here, it's really hard to tell, I'm just going to assume it's this dashed line, although you have negative velocities, that velocity starts getting a little bigger until you get to 0. So what'll happen here is you're going down a little more negative, and then you start returning back to a velocity of 0, and then that thing is just going to be a velocity of 0 like that. So that's roughly what that velocity function would look like, as you have velocity values that are positive, velocity values that are negative, velocity values that are 0. Remember, I'm basing that on tangent lines, okay? So that's what's real critical in that problem. So now what we're going to do is we're going to use this graph to answer a few questions about acceleration. Okay, now what I'm going to do on this, I'm going to take just sort of a snapshot of what I just did here and put this over to the side so I can write over this a little bit. Okay, so I'm going to squeeze this thing right in over here somewhere. Okay, and I'll move this over and I'll show you kind of what I'm after with the acceleration. Okay, so when is the acceleration positive? Now remember, the acceleration would be the slope of a tangent line of the velocity function. So here's the graph of the velocity function right here. So let's just think about, okay, when is the slope of the tangent line positive? So it looks like the slope of the tangent line is positive on the velocity function from 0 to, and let's just say 7, okay? So it looks like you have positive acceleration from 0 to 7, okay? The other thing is you're also going to have what will happen here. Now, remember, we're looking at this graph, not the original. Then you start having a negative sloping tangent line all the way through here until you get to that point there. So it looks like from, let's say, 7 to, let's say, 23. It looks like from 7 seconds to 23 seconds, the slope of the tangent line on the velocity is negative. So in that region, we're going to have negative acceleration. So what we have is positive acceleration there, negative acceleration there. Now what happens? We start having positive acceleration again. Okay, so it looks like from 23 to 27 seconds, hold on, that would be up here. So from 23 to 27, it looks like we also have positive acceleration. Okay, that's it. Now, when is the acceleration 0? So what do you look for then? Well, of course, you look for where the slope of the tangent line on the velocity is 0. So that looks like from 27 seconds to 30 seconds, it looks like there's 0 acceleration. That would be constant velocity. Okay, and if the velocity is 0 right there, then that, of course, would mean that the object's not moving. Okay, so when are we speeding up? That would be when the acceleration's positive. So that would be, we already answered that, 0 to 7 seconds, and then from 23 to 27 seconds we're speeding up. When is the velocity object slowing down? That would be when the acceleration's negative. So that would have been from 7 to 23. Okay, so that's the kind of problem that I expect you to be able to do, is look at a position function and be able to analyze that so you clearly understand where the velocity is positive, negative, and 0. Be able to sketch a graph of the velocity, and then be able to figure out questions about the acceleration based on the graph of the velocity. Okay, the key thing to remember is this. So the velocity is the slope of the tangent line of the position function. And then the acceleration is the slope of the tangent line of the velocity function. That's how that goes. All right. So let's move to the next page. I'm going to have you pause the video and try a problem like this. So just kind of repeating the same thing here, and then this will close off this part of the video. So go ahead and pause here and see if you can do what I did in the previous example on this example. So I've given you a graph of a position function, and see if you can answer these questions. Okay, so let's check and see kind of what you got here. I'll go through and explain some things. To me, the simplest part of the problem probably is this part, A through B. So I kind of just looked at this on here. There's a couple of things that are kind of important on this. When you look at this position function, well, the velocity is positive from 0 to 30. Okay, you have a positive sloping tangent line. But one thing that happens here is from here to here, you have a constant velocity. I mean, that's just a line, so that's constant velocity, all right? Then the only place where the tangent line is 0 would be at 30 seconds, so that's when the velocity is 0. And then the velocity is negative from here to here. So you have negative sloping tangent lines from there to there. Okay, so the velocity, you're looking at the slope of a tangent line of a position function. So we have positive sloping tangent line, 0 sloping tangent line, negative sloping tangent line. So that's how we know this, okay? And this would really mean that we're going in the positive direction when the velocity is positive. From 30 to 60, we would be going in the negative direction. So we may be returning back to our original place. And then the velocity would just be at that maximum right there. Okay, so the next thing I want to kind of focus on is the same thing kind of happens here too. from 40 to 60, you also have a constant velocity. So you could actually compute that based on this. So what I went ahead and did on this is, and I'm going to break this down kind of like this. What happens is when I graphed the derivative was equal to 0 at 30. So you have to have a dot. You have to have the point 30 there on your derivative. That's the only place where the velocity is 0. And then this has to be constant here. So from 0 to 20, it's constant, and the rise is 100. The run is 20. So it's up 100 over 20. So you get a specific velocity of 5 meters per second. That's why I did a horizontal line. That's not really drawn to scale, but 5, that would just be constant velocity right there. And that velocity is rise over run because it's slope of tangent line. Then what happens is in this little piece right here, well, the velocity is positive, but it's decreasing. So what's happening from 20 to 30 is the velocity is getting smaller, so it's going towards 30. That's not constant velocity. The slope of the tangent line is changing in that interval, see? Okay? Then what happens is you have a constant velocity from 40 to 60. Again, the rise is down 100. The run is 20. So that would end up being a down 100 over 20 would be negative 5 meters per second. So from 40 to 60, you have a horizontal line like that. Okay, and then this little piece right here, you have a negative velocity. But what's happening is once it gets to 40, then it becomes constant. Okay, so that's how that goes. So notice on this that you're above the x-axis from 10 to 20. That's a positive velocity of 5, and it's constant. From 20 to 30, you have a positive velocity, so the graph of your derivative will have positive y values. When at 30 seconds, the velocity is 0, so you have an x-intercept. And then the rest of the way, it's negative, so all of these have negative y values. But your velocity is constant in those two places right there. I'm not sure, I hope you caught that, but if not, that's something that you want to learn from. Okay, now we're going to look at the velocity. So what I'm going to do on this or the acceleration, I'm going to take a little snapshot of the graph of my velocity, because that's how I'm going to answer questions concerning the acceleration. Okay, so let me just bring this over here, kind of zoom on this a little bit, and show you how my thought process goes on this then. Okay, so remember the acceleration's positive where the graph of the velocity is positive. And if you look at this is the graph of the velocity right here. This thing right here, that whole curve right there that we just drew. Okay, so the slope of the tangent line from here to here would be 0. So you'd have 0 acceleration right there. From 40 to 60, you would also have 0 acceleration. From here to here, you have a negative sloping tangent line, so you have negative acceleration. There's no place where the graph is increasing, so there's no place where you have positive acceleration. So the acceleration is never positive. The acceleration is negative from 20 to 40. Clearly, that's where the tangent lines are negative. The acceleration is 0 from 0 to 20 and 40 to 60. The object's never speeding up because the acceleration's never positive, but it's slowing down wherever this slope of the tangent line is negative. So those are the answers to that problem. Okay, now this is good stuff. This is really thoughtful, and it helps you really understand how derivatives work as a rate of change as related to position, velocity, and acceleration. Okay, so I'll close this off and post this, and then the last part of the video will be some economics. So good luck. Have fun.